Awesome. Thank you, Alexi, for having me. Great to be here. Hello, everybody. My name is Sarah Robinson. Just make sure my slides are all set here. One sec. There we go. I'm going to be talking about machine learning design patterns, which is an O'Reilly book that was published at the end of last year that I wrote with two of my colleagues, Lack and Mike. So I'm a developer advocate at Google Cloud focused on machine learning. So as a developer advocate, my job is to help educate and inspire external developers, customers, and teach them how to use all of the great machine learning tools that we have on Google Cloud. And we do that through live demos, presentations, blog posts, videos, demo code, etc. Another important part of that job is taking feedback from the external community, folks like all of you, and bringing that back to our product teams. So you can find me on Twitter at srobtweets. I also have a personal blog where I blog about machine learning things at sararobinson.dev. I'll link to it at the end. So with that, I'll get started. And I also have a real life copy of the book right here. So what are design patterns? So design patterns is a pretty common term. That's basically just a formalized best practice to solving a common problem. It's definitely not specific to machine learning. Design patterns, have been applied to many different aspects of software engineering and other fields. In this book, we detail 30 different patterns that the three of us have seen after working on machine learning products at Google, working with customers that are using these products. So in this talk, I'm going to be highlighting 3 different patterns. So this is just a quick preview of a diagram that we have in the end of our book that shows the interactions between different patterns. So it's often the case that you wouldn't just use one of these patterns in isolation. A lot of times they go hand in hand with other ones. And I'll talk a bit about the connections between patterns as I go into the 3 that I'll be highlighting today. So the first pattern that I'm going to be talking about is rebalancing. The number 10 is not a mistake here. This is the 10th pattern that we cover in our book. So just to give you a little bit of context of where it fits into the rest. So this pattern is related to getting your data set ready before you train a model. The last 2 patterns that I'll be covering focus more on productionizing machine learning models. So let's start with rebalancing. And in our book, for each pattern, you'll notice if you've read it or if you're in the process of reading it, each pattern follows a similar structure. So we start by defining the problem that a pattern solves, and then the bulk of the section on that pattern is focused on the solution. And then finally, we discuss some trade-offs and alternatives for that pattern. And there is a GitHub repo that's associated with our book. So for any of the patterns, you can go take a look at a notebook, run some code that shows an example of how to implement that particular pattern. So the problem that this rebalancing pattern is solving is that most real-world data sets are not perfectly balanced. So maybe you've seen, like a machine learning tutorial or a Hello World example where you're given a data set that has a nice, neat number of examples per class. So maybe it's a classification problem, and there's exactly 1,000 examples for each class in your classification problem. That's great, but often the case in real-world data is that the data is not going to be balanced. So examples of that are cases like anomaly detection, where you're trying to detect anomaly. The nature of an anomaly is that it's not very common. So this is an extreme example, the one I'm showing on the right. This is just a data set that we've made publicly available in BigQuery, our enterprise data warehouse on Google Cloud. And you can see this is a binary classification data set. So there's 2 classes. This is used to solve a fraud detection problem. So a common case of imbalanced data sets is fraud detection in financial services. So you can see in this data set, this is just showing a count of how many examples per class. Less than 1% of the data contains examples of fraudulent transactions. So one thing to be aware of here is maybe you train a model on this data and don't make any modifications to the data set or model, and you see your model reaches 99% accuracy. That sounds good when you first look at it, but it's likely a case that the model is just randomly guessing the most common class because it occurs 99% of the time. So just something to be aware of. So yeah, we can see that this data set is quite imbalanced. One thing I want to note before I dive into this pattern is there's a few different types of bias. So bias is often a bad thing, but not always. So in this chapter, in this pattern, I'm focusing on what we call naturally occurring bias. So this is bias. These are scenarios where the data that you're dealing with is inherently imbalanced, and it's not possible to go collect future data, further data. So in the case of fraud detection, for example, you notice your data set's imbalanced. That's just the way it is. You can't go collect more fraudulent examples because there are none. Unfair bias occurs when the data you've collected doesn't accurately reflect all the possible people who could be using your model. So an example of this is, you can see with the emojis, let's say you decide to build a model that detects cat breeds, different types of cat breeds. Your model performs really well, you deploy it to production, people start using your app to classify dog breeds. They're uploading their dog photos. Your model wasn't trained on that data, but it's going to give a classification of a cat breed anyway. In this case, this could have been solved by further data collection. So we have a different pattern that focuses on unfair bias, called the fairness lens pattern in the last chapter of our book. For this rebalancing pattern, I'm focused on naturally occurring bias. So I touched on this a bit in the first slide, but it's really important when you're dealing with imbalanced data sets to choose the right evaluation metrics. So let's say we finish training our model, we see accuracy is 93%. Maybe for our particular use case, that's okay. We've decided that, if it's above 90, we're okay with that. But the problem with just using that blanket accuracy number as the metric is that you might be missing some problems with your model. So if we look at the accuracy breakdown by classes, we can see that this particular model was only able to classify minority class data correctly 12% of the time. Here I'm just using the word majority class to refer to, this is a binary classification example. So majority class is the class that has the most data available for it. Minority class is the least. So it's really important to make sure you're using the right metrics to evaluate your model. If we were just using accuracy, we might decide it's okay to deploy this model, when in reality, it's not performing very well at all. So now that I've addressed the problem there, what are some techniques for handling imbalanced data? There's many more than what we've detailed here, but these are the three that we focus on in the book: downsampling, upsampling, and weighted classes. So I'll dive a bit into each one. So downsampling. So let's say this is what our data looks like at the start. We have, way more examples for a particular majority class. So what downsampling does is you randomly discard a sample of the majority class data. And as you can see, this significantly improves the class balance in your data set. Some things to be aware of with downsampling. In order to do this, it obviously requires that you have a big enough data set to begin with. And when you're doing it, you want to make sure not to lose meaning or relationships that are conveyed in the majority class data, because there's still relationships you want your model to learn about that class. So you don't want to lose important information. So it's important when you downsample that you do that randomly, and that might look different depending on the type of data you're working with. So if you're dealing with data that has a time column, for example, you probably don't want to just remove a chunk of data. If the data is ordered by time, you don't want to remove the last chunk of data, because that's going to take away some meaning from the data set. So you want to be careful about how you randomly discard that data. Just one thing to note about downsampling. So you're left with, ideally, a much better balance of your data. The next technique that we talk about is upsampling. This one is a little bit more complicated than downsampling, but it's essentially the reverse approach. So you start with this very imbalanced data set, and the idea here is that you use the minority class data that you have available, and you generate new data that's based on that. So this new data should be in the same feature space as the existing real data that you have. There's a paper that proposed this technique called SMOTE. It stands for Synthetic Minority Oversampling Technique. Really interesting paper, definitely recommend checking it out. So a simplified example of how it works is this. This is just an example from a data set that predicts, it takes some health metrics on a person and predicts whether or not they'll develop a certain health condition. So on the left, we have 2 real data points from the minority class of this data. And then we've used that. In this case, we're generating a new synthetic data point that's the median of these 2. So a simplified example of how SMOTE works. And there are some Python libraries that can help you do this. So in the case where maybe you wanted to try a downsampling, but you just didn't have enough data available in your initial data set, then SMOTE might be a good technique to give a try. So the last approach for handling imbalanced data that we discuss in the book is weighted classes. So weighted classes, you can imagine this as your minority class speaking to your model saying, pay more attention to me. Obviously a simplified example of how it works, but basically you want to tell your model to assign more weight to the minority class in your data set. And here's an example of how you would do this in Keras. So the way that you determine how much weight your model should assign to given classes is based on the balance of that data set and how that data set, how many examples of each class are in the data set. And then all you need to do in the Keras example is just pass this class weights parameter to your model, and you can assign class weights that way. Other ML frameworks have different ways to do very similar thing. If you want to pass class weights, for example, in XGBoost, PyTorch, there's ways to do that. So to summarize the rebalancing pattern, we talked about 3 techniques for handling imbalanced data. The good news here is that you don't have to use just one. So you could actually use all 3 at once. Let's say you had enough data to do downsampling. So maybe you wanted to downsample, remove a random sample of your majority class data, but not all of it. You could do that. Then you could upsample to account for the remaining data imbalance. And then finally, you could use weighted classes in combination with that. So it's definitely worth trying different ones to see what works best on your data set and what works best for your model. So that is rebalancing. The next pattern that I'm going to talk about is workflow pipeline. And this is pattern number 25 out of 30 in our book. So the idea with workflow pipeline is bridging the gap between model development and deploying a model to production. So when you're developing a model, you're doing data pre-processing, you're validating your data, training your model, deploying it, but you don't just build a machine learning model once, deploy it, and you're done. That's just not how it works. You have to constantly monitor your model, make sure that it's still performing well on new data, handle how you're going to retrain data, new data that becomes available, and use that to feed back into your model training. So you're constantly running a series of experiments. And maybe you don't want to run the entire process again, but maybe you have new data available. So you need to run part of this workflow again. So you need to do data pre-processing, iterate on your model, and train it. Or maybe you just need to retrain your model and deploy a new version because maybe the framework you're using has changed and you want to take advantage of some new features. So it's an iterative process. And when you fix all these small things, it's easy to lose track of all these changes that you've made, especially if you're working as part of a larger team. So, just the end-to-end process in development can work on its own if you're the only person building the system or, there's very few people on your team. But once you start to have a lot of people working on a model or problem and maintaining that model in production, it becomes a little bit unwieldy. So one way you could solve this is you could just take the entire end-to-end process that we talked about from data preparation to model deployment and just make it a job and then just rerun that job whenever you need to. The problem with this is that it can be pretty wasteful. So if you're repeating certain parts of the process many times, for example, to do something like hyperparameter tuning, that can use a lot of compute resources. So it has some wasteful repetition. You don't necessarily need to rerun the hyperparameter tuning step of your workflow every time if you've just collected new data and you want to retrain a version of your model. And so there are some similarities between MLOps and DevOps, but there are also some key differences. So with MLOps, you're not only testing and validating code, because you're doing that as well, but you're testing and validating data, your data schema, and your models. And ML is also concerned with the process of automatically monitoring, retraining, and redeploying models. So you have to take work to ensure that your model is still performing well in production, and take the necessary steps to update the model. And you're also not focused on a single piece of software. You're dealing with an entire end-to-end ML system. So you want to make sure that your workflow is repeatable also. So you want somebody on, in a different location to be able to rerun your end-to-end ML workflow and have the same outcome. So just highlighting some ways that MLOps adds to DevOps. So to solve this, we have the concept of workflow pipeline, which is the name of this pattern. So here we're looking at a screenshot of the DAG for a pipeline that's running in Kubeflow pipelines. This is just one example. There's many different tools and frameworks you can use to implement ML pipelines. But the key concept here is that it's a directed graph of ML steps. So each step in this pipeline, in this DAG, is a key step in your machine learning workflow. So this is just what the dashboard looks like for an example pipeline that we're running in Kubeflow pipelines. And a key component of this is that each step in your pipeline is its own container. So here we have our container for data pre-processing and validation. We have our container for feature engineering, for training models, for evaluating our models and picking the best one, and then finally for deploying our model. So each of these steps is its own container. And the idea with the pipeline pattern is that you link all of these containers together to create one workflow pipeline. So why would you do this? Why is this helpful? This can help you group all of your steps into a series of experiments. So you can launch this pipeline end to end as a whole. But the important part here is you can also launch individual steps of your pipeline. So maybe you just want to run the hyperparameter tuning step of your pipeline in isolation. You can do that really easily with following this pipeline pattern. And then another important part of what this pipeline pattern does is it allows you to track dependencies from each step as you go through a particular end-to-end pipeline. So these steps are not independent of each other. Each step generates some artifacts and then feeds those artifacts into the next step. And then the next step will look for a particular input. And the idea is that all of these artifacts are stored in a central location so that you can track what was generated from a particular pipeline run. And you can track the artifacts that were generated when someone else ran your pipeline as well. So the hyperparameter tuning step might take the output of the pre-process step, the engineered features, and then feed that into the model for training. So this allows you to reuse artifacts. So maybe if you're only running one step of this pipeline, you can reuse the artifacts that were generated the last time the previous step run, if the data changes. So another benefit of pipeline is this artifact lineage tracking, so that you can see what was generated every time your pipeline runs, and it becomes much easier to manage this way rather than just running ad hoc experiments. So how will you implement this series of containers that you link together? So you could write the code to do that yourself, to handle all the dependency tracking and storing and managing artifacts. But instead, in the book, we recommend using some frameworks that can help you with this. So there's many different pipeline frameworks that you can choose from. Most of them are open source. And these are built to help you with this process. And they also come with many different pre-built containers. So in the workflow pipeline section of the book, we talk about TFX, TensorFlow Extended, an open source framework for building ML pipelines. So you can write the code in Python. You don't have to worry about creating these containers that are underlying each step yourself. The framework will handle that for you. So what TFX does is it also provides a library of pre-built components. So for common things like let's say you want to ingest data from a CSV or ingest data from BigQuery, like we see here. You don't have to worry about writing the boilerplate code to read that data and decide where you're going to store it, et cetera. Frameworks like TFX will handle that for you. So in this example, TFX has a pre-built BigQuery example generator component. And all you need to do is pass that a query. You can pass it a separate query for your training, your validation, and your test data if they're in separate tables. It'll take care of running that query, grabbing the data, and putting that data in the location you specified for where you want to store the data for your pipeline runs. So the code we see on the top is how we're defining our pipeline. The important piece here is the components. So we define all the different components that make up this pipeline. In this example, all of these components that we're using are pre-built components that are part of TFX. So we just need to provide a couple parameters to those components that are specific to our model or use case. So in this example, our first component is BigQuery generator. This takes care of reading our data from BigQuery as our data source and writing that output to an output file. In the example in the book, we talk about using cloud storage to write that data, but you could store the output of the artifacts of your pipeline wherever you'd like. So then the next step in the pipeline is this statistics generator component. So this will read the data from the BigQuery example generator and give you some overall general statistics on that data that you can see in the dashboard. Finally, that gets fed to a component that generates the schema that will be feeding into our model. We train our model and then we deploy it. You can also have some conditional aspects here. So maybe you only want to deploy a model if it reaches a certain accuracy threshold. So you could then add an evaluation component in between the train and model pusher component. So there's lots of options for customization here. The key idea of the workflow pipeline pattern is that you want to capture your machine learning workflows in a DAG, and this pipeline is executable as a whole or in smaller parts. So if you only want to run maybe 2 or 3 components at once, you can do that as well. One thing I forgot to mention is that in addition to this idea of lineage and artifact tracking, there's also logging and monitoring for each step of your pipeline. So I think I showed in a previous slide, you can see the logs for individual steps right in your pipeline's dashboard. And this is pretty common between different pipeline frameworks. One of the great things about using these open source pipeline frameworks is that you can run your pipeline wherever you'd like. So you could run your pipeline on premise. You could then take the same pipeline code and decide to run it on different cloud providers. So using these open source pipeline frameworks can really help with that. Everything runs as containers, so this ensures repeatability. It also makes it so that, and TFX and many of these frameworks have the ability to obviously write your own custom containers. So if custom pipeline steps, so if the pre-built steps don't do exactly what you want, you can define your own custom step for some custom task you'd like to define in your pipeline. It also kind of separates concerns so that, let's say you're in charge of data collection and feature engineering. You can go off and work on that separately. Maybe the MLOps team that's in charge of deploying your model and running continuous evaluation, they can work on that separately and use different dependencies for those particular steps. And then you can combine that work together into this pipeline. So this allows for more efficient development and productionizing of models and tracking each step of the ML process from end to end. So when you're starting out, maybe it makes sense to just, iterate this workflow on your own within a notebook. But pretty soon after that, I find it really helpful to turn that workflow into a pipeline so that you can more easily share it with others on your team and track the output from certain runs and make it reproducible and repeatable. So that wraps up the workflow pipeline pattern. The last pattern that I'll be covering is feature store, which is the 26th pattern in our book. So what I talked about before with the pipeline pattern, it's common at an organization that's doing a lot of machine learning tasks. You likely won't have just one pipeline that's doing one prediction task. This happens in toy problems, but more likely is your organization is solving many different tasks using machine learning, and these different tasks may be run by different teams. So in production systems, you commonly will have more than one pipeline, more than one prediction task at play. But oftentimes, these different models and prediction tasks will be using the same data. So let's say you have multiple teams building different types of ML models, and let's say they're all running their own pipelines, writing that code from end to end. This ad hoc approach will quickly become kind of unwieldy, mainly because they're not reusing features. So let's say, for example, that you're building a model to predict whether or not a customer will return an item. And as input to that model, you have a feature that's a windowed aggregation of purchase data. So you're using that as a feature, but chances are there's another team that's solving a different prediction task, and they're using that feature too, but they're computing that windowed aggregation on their own, doing it separately in a slightly different way. So in that case, effort and time are wasted because those teams could be sharing that feature engineering code and pulling the features in the same way from your database, but they're not. So that effort is duplicated. So this approach of all these disparate teams building models and engineering features in their own way won't scale. Some other problems that will arise when this happens is you might run into some issues for data governance when you're dealing with sensitive data. So maybe you have data that user data that your ML model is using, and you only want certain teams or certain groups of people to be able to access that data. If you have more than one team doing feature engineering on that data, it's harder to control that. So features are not easily shared between teams or across projects. Another problem that arises when you're not sharing features across these different ML problems is a problem called training serving skew. So ideally, you want the feature engineering techniques that you're using for training your model to be the same as what you're using when you're serving your model in production and doing online near real-time predictions. So you want that feature engineering to be the same so that there aren't inconsistencies between training and serving. So generally, it just becomes difficult to productionize your features, to move from training and serving, and you need a framework that will support low latency inference when you're getting predictions on your model online, but you also want a system that supports high throughput for training when you're dealing with large batches of data that you need to run feature engineering on. So that's the problem that the feature store design pattern is solving. So what is feature store? It's essentially the idea of creating a centralized location to store and document feature data sets. So you can think of the feature store as implementing basic principles of software engineering, like versioning, documentation, and access control. But it's doing this for machine learning features. So there's a few key components to a feature store. I touched on this before, but the first one is that it's able to do both batch and streaming. So you need to be able to store and serve features for low latency inference and serve them very fast. But for training purposes, you're dealing with large batches of data. So you want your feature store in this part, you would put your data in a data warehouse and you would interact with large batches of feature data that way. There's also a metadata layer to many feature stores that lets you version your feature sets. So let's say you have an older version of your model, new data comes along, you come up with a new technique for engineering a particular feature and you want to use that on new models, but you want your old model to continue using the old version of the data. In that case, you can version using this metadata layer that's available in many feature stores. It allows you to version your feature sets. The older models will continue using older versions of the features, and newer models can use the newer versions with the new techniques for feature engineering that you've come up with. So essentially, you can think of a feature store as a dual database. So it's a data warehouse of features for machine learning. But in this case, it has two use cases. So you need to be able to support online inference for prediction, and that needs to be low latency. But you also need to be able to handle doing feature engineering on large batches of data for training your model. So we have this idea of this online database that's interacting directly with your online application, that's pinging your machine learning model. That needs to be able to do this feature engineering very fast in near real time, but then you have this offline database of features, which is what you want to use for running training jobs to train large amounts of data. So we have these two key design characteristics of pretty much any feature store. So you need a tool that processes large engineering jobs quickly, and a way to store features for low latency and high throughput. So you have this offline feature store that handles large batches of features, and then you have this online feature store that will serve a single row of features. So maybe you're converting raw text to embeddings, and you need to feed those embeddings into your text classification model. So in this case, you would use the online feature store when you have a user using your application, entering some text into a text field. Maybe it's auto tagging that text. So you need to be able to do prediction on that one piece of data really fast. In that case, use your online feature store. You don't care as much about low latency when you're running training jobs, because you don't likely need to run those, multiple times a day or even every day. Maybe you're training a new model weekly or monthly. So latency isn't as important in that case. So then you use your offline feature store for model training. So moving along, feature engineering jobs are typically set up using services like Spark, Beam, Apache Flink, Scala, etc. And your offline feature store might use Hive, BigQuery, or Cassandra to store the data. So BigQuery's service provided by Google Cloud, and you typically use an enterprise data warehouse for this offline part of your feature store. And then the online feature store optimizes for low latency. And then finally, many features have this metadata layer that you can use to version different sets of features. So in the book, there's a lot of companies have built their own feature store. Some of them have open sourced it. In the example in the book, we talk about a specific open source feature store called Feast. Feast was developed in collaboration by Google Cloud and Gojek. Gojek is a ride sharing company. So for streaming ingestion, Feast uses Apache Beam. For fast online serving of features, it uses an online store called Redis. So you can check out in our GitHub repository for our book. We have examples of how to set up a feature store using Feast. You can also go directly to the GitHub repo for Feast and check out the getting started instructions on there. So just going to show quickly a couple code snippets that show how you would register a feature set in Feast, ingest the data, and read the data. So for this particular example, we're referencing a taxi rides data set that has some lat-long data on taxi ride, the fare, along with some other metadata on the ride. This is a public data set that's available in BigQuery if you're interested in checking it out. And this is what we use in the example in the GitHub repo. So the first step is to connect to a Feast deployment, and then you create your feature set. You connect the feature set to your data. So in this case, we're loading a CSV from Pandas that has our taxi ride data. and we're telling Feast where to load our data from. Then we do our feature engineering, and we infer the features of our feature set from this pandas data frame that we've specified. We register that feature set. We ingest the features into it. And then the next step is to retrieve our data. So we have two APIs here, one for this online retrieval of data, and then one for getting our batch features. And these are, you can think of these as two entirely separate REST endpoints. But the great thing about using a feature store is that it's going to make sure that both of these features are consistent. So this will help you avoid situations like training serving skew, where you're using a different method to do feature engineering on data for training versus serving. So you have these separate endpoints, the separation of concerns between model training and model serving. But the feature store is making sure that both of these are consistent. So this is the code for how you would do offline batch retrieval of features using Feast. And this code shows how you would do that for online serving of features. So kind of brings us to the end of these three patterns from our book. So just to summarize, the first pattern that I talked about was rebalancing. This solves the problem of real-world data sets not being perfectly balanced and how to account for that when you're pre-processing your data and training your model. The three techniques I talked about were downsampling, upsampling, and weighted classes. And you don't have to use just one, you can use many of those. There's other solutions for handling imbalanced data as well that weren't covered in the book. And then the second pattern I talked about was workflow pipeline. And the problem this is solving is needing a way to run different end-to-end trials for different steps in your machine learning workflow independently, but at the same time, being able to track the output of each step and have a central artifact store where you're able to see the artifacts that were generated by each step. So the way that you solve this is through workflow pipeline. You make each step of that ML workflow a separate containerized service. Again, there's many libraries that can help you out with that. Kubeflow pipelines and TFX are both great ones. And then you can run that pipeline with a single REST API call. You can also set up triggers. I'm not sure if I mentioned this when I talked about the pipeline pattern. So maybe you want to trigger your pipeline to run end to end whenever you have, let's say, 5,000 new examples of data available. You can set up a trigger that will just run that REST API call to kick off your entire pipeline whenever a certain condition occurs. And then finally, we talked about feature store, which solves the problem of disparate teams all doing feature engineering with the same data on their own, which can be a waste of effort and time and can lead to work stream inefficiency. So the solution there is to create a feature store, which is a centralized location that will store and document your feature data sets to handle both batch use cases for training models and doing feature engineering really fast for online use cases. So quick summary of the three patterns I talked about. If you're interested in buying the book, it's available at this bit.ly link. Cool thing about the book is that all the royalties from it are going to Girls Who Code. So we're supporting a great cause. There is a free trial to read online at the URL here. Lack and I are both on Twitter. So if you have questions, want to learn more, questions on the patterns I talked about, reach out to us on there. And finally, we have our GitHub repo that has examples of implementing each of these patterns. So with that, I think we have a few minutes for questions. I'm going to hop back to the Zoom.
Yes. Before I ask you questions, and I want to remind that if you want to ask a question in the live chat, there is a pinned link that you can just click. It will bring you to a slider, and then you can ask any question. But before we do that, I want to announce the winners of your book because we had the raffle.
Oh, awesome.
So I want to quickly share my screen and just show you that these 5 people won the book, and I will get in touch with you, and I will ask you for emails, and then you will get a free copy. And you
Congrats,
can read,
folks.
yes, you can read all about these three patterns and all the others. Yes, so thanks for taking part, and congratulations. Yes, and thank you very much, O'Reilly, for providing us free copies of the book and supporting this conference in social media. Yes, so now we have a few questions.
Are you using the chat on Zoom, or you're just going to read the questions?
Yeah, I'll read the questions.
Okay, awesome.
Yeah, but maybe before I read the questions, we already have like 5 questions. I have a question of like my own question. I'm curious, like, if you can select 1 or 2 patterns that you would recommend to learn for people who are just starting in data science, which patterns would it be?
That's a great question. Yeah, so we went in the book in such a way that you don't need to read it end to end if you don't want to. You can kind of pick and choose which patterns are relevant to things you're implementing. I'll also note that the book isn't recommended as like an ML 101 book. It assumes some familiarity with basic ML concepts. That being said, some good patterns to get started with are probably patterns like I'm just referencing the book right here. I don't have the 30 patterns memorized, but I would say probably chapter 2 goes into data representation design patterns. And so a lot of the patterns in there will be especially useful if you're new to machine learning. Thinking about how to represent different types of inputs for machine learning. So whether you've got, tabular numerical data, you're dealing with image data, you're working with text data. There is a pattern that talks about how to combine different, let's say you have a model that accepts like text data and tabular data together. So yeah, I would start by looking at that chapter. Another thing you can do is our last chapter. So it's definitely designed to be able to hop around between chapters. The last chapter is a summary chapter, and it talks about some examples of how you could connect different patterns for certain use cases. So it goes through a few common ML use cases like anomaly detection or natural language processing. So you could start there as well and just see which use case looks most interesting to you or matches what you're doing. Choose some of the patterns from there and then jump around. So curious to hear what folks, if you've read it, like which patterns are most helpful to you, which resonated. Great question.
Should they tweet and mention, or how can they let you know about that?
Oh yeah, Twitter's probably the best way. SRob tweets, just find me on there. Let me know your favorite pattern. Tag LAC too. We like to hear what readers think of the book.
Yeah. And what would you recommend somebody, like let's say somebody is data scientist who already knows how to train machine learning models, but they want to move into machine learning engineering, right? So to get more into these engineering aspects, productionizing models, what are the 1 or 2 patterns would you recommend them to focus on? Like, let's say they know the basics of machine learning, but they want to,
Yeah, that's a good question because the book talks about different roles. So it applies to, anyone from a data scientist to an ML engineer who's in charge of deploying models, maintaining them. So I'd recommend probably some of the MLOps patterns for someone who wants to learn more about that. So specific examples, I would say model versioning is a good one. That's the idea of deploying different versions of a model to different REST endpoints. Another really important one I'd say is continued model evaluation, which talks about how to set up a system for ensuring that catching data drift or model drift, which basically just means that your model is no longer fit for purpose because you can't really just train your machine learning model, leave it there and be done. You need to implement some sort of system that's able to see how the model is performing on new data that's coming in to make sure that it's still accurate. So one example is, let's say you have a model that's predicting flight delays, flight patterns, the way that airlines time flights change over time. So if you train a model on 5 years of data from 5 years ago, chances are that that model is not going to be performing well now as companies adapt. So that's just one example. But yeah, I'd say continued model evaluation and model versioning.
Okay, thank you. And then we have quite a few questions. So first question is, what is considered a pattern? So maybe it's a bit of a dumb question, but I want to know what the book encompasses.
No such thing as a dumb question. What is considered a pattern? So a pattern, at least how we define it, is a common practice in machine learning. So some of these patterns, we've gotten this feedback from a few people who've read the book, is they have implemented one of these many times, but they just weren't able to put a name to it. So just things that we've noticed again and again in different machine learning workflows, and we've kind of condensed that into just a best practice for solving a particular task. So I would just say it's a method for solving a particular task. And you saw some examples of the three I presented, but they all follow that similar format. A common task in machine learning. So a lot of these patterns could apply to many different types of models. So something that's widely applicable and fairly common, I would say, is how we define a pattern.
Yes, thank you. And then a related question is, like I first heard about design patterns in programming. And is there any relationship between the software design patterns and the machine learning design patterns?
Yeah, I would say they definitely relate. I mean, design patterns, and we talk about this in the intro, design patterns, that term has been used for many years, and it applies even outside software engineering or tech. Design patterns could be applied in the medical field. In probably any industry has a number of common design patterns. There are some connections, I'd say, between ML specific design patterns and more software engineering design patterns. But I highlighted some of the differences in the workflow pipeline pattern, because MLOps takes some common patterns in DevOps, but adds things to them. So in ML, I'd say the key difference is you not only need to make sure that your code runs correctly, but you have this added step of doing all sorts of validation on your data and your model. I like that about ML. It presents an interesting challenge. So even if, let's say you've written your model code, the code is great, it runs perfectly, no errors. But if your data is not good, then you're not going to have a good model, even though the code runs perfectly end to end. So I think ML builds on a lot of the design patterns you might see in software engineering.
And you just answered the question from Alex, who asked what is the reason for separating DevOps and MLOps, and I think you just answered it, right? So maybe you want to add something to that, or you covered that video?
Yeah, I think I covered that. I think the main differences are additions rather than differences. So it's taking all these DevOps principles, things like continuous integration, continuous deployment, and adding to them. So you also have, in addition to that, you have continued model evaluation, like I talked about, making sure that your models don't become stale. The meanings of things in your features, or the target variable, the thing you're predicting, might change. So I'd say, yeah, the biggest additions are continued model evaluation and retraining.
Mm-hmm. And versioning, is it something that is also an important part of MLOps, or?
Sorry, what did you say?
Like versioning, like model versioning, data versioning.
Yeah, definitely. We have some patterns on that as well. So we have a pattern on data versioning. It's called bridged schema. This is how you handle updates to your data schema. So not just versioning. So there's the concept of versioning data where the columns haven't changed. In that case, you just have more data that you're dealing with. But this pattern deals with a particular use case of where your schema might change. So the example it goes through is, let's say you have, going with the taxi example, let's say you have a payment type feature in your data set. And historically, the possible values for that were cash or card. But now you have new data available, and you're able to get more specific. So instead of cash and card, you have cash, credit card, debit card, or gift card. So this pattern talks about how to handle bridging that new schema with the older schema to train your model. So that's an important one. And then model versioning talks about how you can version your deployed model so that clients that want to continue to use the old version can call that endpoint, and then you can deploy new endpoints. And then when they're ready to upgrade, they can use that one. That one's also important because it separates concerns between the data science team and the app development team. So by versioning your model, the team that's in charge of deploying your application and writing that application code, they don't have to worry about, what framework is this model built with? What do the exported model assets look like? All they need to know is there's a new version that's available at this endpoint.
Yes, thank you. Then we have a question about these design patterns in the book. Are these design patterns Google Cloud specific in terms of trying out or not?
Good question. So none of the patterns are Google Cloud specific. When we introduce each pattern, we talk about the problem and the solution, and we're describing that in more higher level situational terms. Because the three of us do work on Google Cloud, when we go through specific implementations of these patterns, you will see a lot of Google Cloud technology that we use to implement them. We use TensorFlow for a lot of the examples, but we also make sure to include some examples with PyTorch, XGBoost, scikit-learn. So no, the patterns themselves are definitely not Google Cloud specific. The specific implementation examples might lean a little bit more towards Google Cloud.
And yeah, I remember even in this presentation, you showed kubeflow pipelines, which is not a part of Google Cloud, right? So this is like an open
right.
source
Yeah,
framework.
kubeflow pipelines is an open source framework for pipelines, along with TFX. So
Yes.
so we do talk about quite a few open source frameworks as well, like Feast also.
Mm-hmm. Yeah, and Feast also runs on other cloud providers, not just Google Cloud, right?
Yeah, definitely. Yeah, so the goal of the way we've set up the book is that, maybe the code snippets become out of date because of a new version of TensorFlow or some service we're using. The ideas behind the patterns still should be very relevant because we talk about them more in, higher level implementation terms of just like when a need for this pattern would arise.
Mm-hmm. And there is a question about this about unbalanced data. Is there any recommendation on algorithm or a design pattern which can work well with unbalanced data without having to rebalance the data?
Oh, interesting. I would say the best solution for that is probably to try weighted classes without downsampling or upsampling, and seeing if that's able to work for your particular use case. Another method could be to change the error metric that you're optimizing for, because I talked about accuracy as one example, but the way that you choose to measure your model's performance will significantly influence how your model performs. So I'd say, yeah, try switching up the optimization objective and weighted classes, and that might work just fine. You might not need to add or remove data.
And if I may add something from me, is sometimes you can rephrase a problem as a search problem. And then instead of, trying to predict a super skewed, unbalanced, like this positive class or negative class, you kind of try to retrieve it to find it. Sometimes it works, sometimes it doesn't.
That's a great point. We actually have a pattern that covers something related to that called reframing. So that talks about, changing a task from, like you just said, from regression to classification. So maybe you have a regression task where you're predicting a numerical value, but you have not very many examples of outliers on either side. So then instead, just bucket your data into a classification task. That way, all those outliers are grouped together. And there's a good chance your model will perform better at predicting outliers that way.
Okay, thank you. I think we will no longer keep you. So thanks a lot for coming. for joining. Sorry, I keep saying coming, but these days we don't come to events, we join events, right? We join remotely. So thanks a lot for joining, for spending time with us, for sharing all this knowledge, and for talking about these design patterns. And yeah, thanks a lot.
Thanks for having me, and thanks everybody for joining. Appreciate it. Have a good weekend, everyone.